Okay, let's get ready for the last video of Unit 3. This last video is going to be on the different types of polarity that molecules can actually take on. So let's start at the top. So what we're talking about is the fact that within a bond, meaning every single bond has some attraction that exists between the atoms that are part of that bond. And they will be sharing electrons. And like we talked about earlier with one of our trends, they won't necessarily be sharing them evenly. One atom may be pulling a little more on the shared electrons than the other. That attraction that exists leads to different types of bonds. And there's two types of bonds. There's polar bonds, and there's nonpolar bonds. So what's the difference? First off, nonpolar bonds, that's where they are equally sharing the electrons. They're both doing the same amount of pull. They're not spending more time around one atom than the other. It's very, very equal, or some very, very close degree of equal. That might be like kids playing a playground, even balancing, and you have the two sets of kids pulling evenly. However, polar bonds or polar covalent bonds, that's when you have an unequal share of electrons. And that tends to make the molecule itself possibly become polar. So since polar covalent bonds are unequal sharing of electrons between atoms, if we look at hydrogen chloride, HCl, they have a very uneven sharing of the electrons. Chlorine would hang on to the electrons more than hydrogen would. One atom has a partial negative charge and the other has a partial positive charge. So in this case, we look at the configuration of these two. The one on the left is your hydrogen, and even though the one on the right says bromine, we're going to pretend like it's chlorine, like is in our example. The electrons would spend a whole lot more time around the bromine because bromine is more electronegative than hydrogen. And since chlorine is so much more electronegative than hydrogen, the electrons would spend more time around that particular atom. So it's like an uneven share where one side, in this case the chlorine, is pulling so hard against the other electron, the other atom, that the electrons spend more time around one atom and not the other. That would be a polar covalent bond. Covalent because it's shared, but now because they're unequally sharing it, that would be a polar covalent bond. So the other possibility is to have non-polar covalent bonds. Now this one's equal sharing. Most of the time this happens when the two atoms are exactly the same or very, very close in electronegativity. So chlorine, ClCl, nitrogen, the molecule, N bond, oxygen, the molecule, O bond. All those bonds, because there's two atoms that are exactly the same, they're going to have the exact same electronegativity. They're going to pull evenly, like these two dogs tearing apart this poor, what looks like a stuffed bear, or maybe a stuffed rabbit. I don't know. Anyway, so that'd be pulling equally on the electrons in the middle. They don't spend any more time around one atom or the other. So if I look at it in general, we have two types of bonds. We have ionic bonds and covalent bonds. Ionic bonds is when the electron has completely left. These are my electrons. They're that might be part of the bond. They completely go over to the one atom and make that one atom negative, make it an anion. And the other that lost the electrons would become positive, and then they come together by electrostatic attraction. That's an ionic bond. But there's also covalent. So if it's a nonpolar covalent, the electrons that are part of this share zone are equally shared and spend the same amount of time in the left circle as the right circle. And then the last possibility is the polar covalent bond. That's where maybe they spend a little more time around this one on the right-hand side. That means this one on the right-hand side will have a slight negative charge, partial, and the one on the left would have a slight positive charge. So if I had to classify bonds as being ionic covalent or polar covalent, one thing that gets used is to look at the difference between the electronegativities of the atoms. So we can determine what type of bond we get by looking at the differences in electronegativity between the two elements in question. The bigger the electronegativity difference, the more polar the bond is. And this is the table that pretty much gives a fair representation of what happens. So if the electronegativity difference is very small, like between 0, non-existent, and 0.4, we consider that bond to be covalent because it's sharing, but also it's going to be nonpolar because it's sharing pretty evenly. The two electronegativities are barely different. If the electronegativity difference is between 0.5 and 1.9, we say that bond is going to be polar covalent. That's the bond. And if the difference is big, like between 2 and 4, we might call that a ionic bond. So let's see how we can figure this out. So what type of bond is HCl? So HCl has, H has a 2.1, chlorine has a 3.1. The difference between them is 1. So that would make this be a polar covalent bond. Now our turn. So if I look at nitrogen and hydrogen, a atom of nitrogen bonds with an atom of hydrogen, would that be a ionic bond or a covalent bond, or maybe polar covalent? So the difference is 9.9. Go back to that chart. 0.9 falls into polar covalent territory. So that means that bond would be a polar covalent bond. How about this one? 2.1 and 2.1. Oh, that's easy. That's no difference. That's going to be a non-polar covalent bond. What about calcium and chlorine? Calcium and chlorine, calcium has a 1, chlorine has a 3. So let's see, that's a difference of 2. That qualifies to be an ionic bond. And of course, a metal and a non-metal is likely to give you a ionic bond. Couple more. What about magnesium and oxygen? So magnesium is at 1.2, oxygen is at 3.5. The difference is 1.3, or sorry, 2.3. So I go back to my table, I look at it, and I say 2.3, that also falls in the ionic category. And again, big surprise, if I look at this, I'm looking at the relationship between a metal and a nonmetal. Last one. How about hydrogen and fluorine? Hydrogen and fluorine, hydrogen is 2.1 and fluorine is 4. That difference is 1.9. 1.9 difference means that that is going to be a polar covalent bond, a very polar covalent bond. So the top end. So we can look up the electronegativities and determine whether a bond is going to be polar or not. So how do we show a bond is polar? So this is what we do. There's two different ways that we do this. One is to use this little delta plus and delta minus to indicate which side has a plus side and a whole side, plus side and a minus side. That charge is not absolute. This is a partial charge. So when we do a little D or that little squiggle, that means it's a partial charge. So delta plus means it's got a partial positive charge, and delta minus means it has a slightly negative charge. It's not going to be a complete charge. There's no charge on hydrogen. There's no charge on the chlorine. There's a differentiation. Another way to show this is with this funny little arrow at the bottom. Note the base of the arrow is a plus. That means that's going to be on the plus side of the bond. And you point an arrow, like a vector, an arrow, towards the negative side. So in this situation, that chlorine is pulling harder on the electrons. The electrons are going towards the chlorine. They're spending more time around the chlorine than they are around the hydrogen. So that's what happens with a bond. A bond can be classified as polar or nonpolar. But what about molecules? So with molecules, we may have a combination of polar bonds that all kind of balance each other out. So a polar molecule is going to have one part of the molecule is going to be slightly positive and one part of the molecule is going to be slightly negative. So this is a combination of two things. One, we need to make sure that the molecule has polar bonds. If the molecule doesn't have polar bonds, then we can't have a polar molecule. You have to have individual bonds have an unequal sharing of electrons. So we can tell whether the bonds are polar by looking at those electronegativity differences. And the second thing that has to happen is we have to have an asymmetrical molecule. What does that mean? That means it's not going to be symmetrical in 3D space. So here's some examples. So the one on the left is polar because it has only one bond, and that one bond is polar to hydrogen and fluorine. So this molecule as a whole would have this side where the fluorine is going to have a slight negative charge. This side where the hydrogen is has a slight positive charge. The molecule as a whole is polar. How about this one? I've got a polar bond here going from hydrogen towards oxygen, a polar bond here going between hydrogen and oxygen. If I look at these two, they both are pointing up. Both are pointing towards one another, but they're also both pointing up. The fact that when you combine these two arrows, you get something that's pointing up, that means you're going to have something that is going to be polar. So this molecule as a whole has two polar bonds that do not cancel each other out and gives us a polar molecule. And here's carbon tetrachloride. This is that tetrahedral shape, and the tetrahedral shape is going to give us a configuration that is very symmetrical, and all the atoms are the same. Every single bond is the same. All the bonds are charged. All the bonds are polar, but the bonds cancel each other out. It's like pulling tug of war in 4 different directions in space and having that central carbon atom not pull at all. So because of the combination of the symmetry of the molecules and whether or not the bonds are polar, we can tell whether the molecule itself is going to be polar or not. For instance, carbon dioxide have 2 very polar bonds. But since carbon dioxide, we said in the last video, was a linear molecule, that carbon dioxide, being a linear molecule and being symmetrical, is going to pull in 2 separate directions, but they're going to cancel those pulls out, so the overall pull of the entire molecule is 0. Same thing's true for carbon tetrachloride. We just saw that. Those 4 bonds all pull equally, and they pull in a symmetrical difference, just a symmetrical configuration. The thing that's kind of not completely true is they're showing this as a 2D model, not a 3D. You know that carbon tetrachloride with 4 bonds would form a tetrahedral shape. And the last one is BF3. Now, BF3 is kind of weird in that it only forms 3 bonds. It does not have a full octet on the central atom, but because all these bonds are polar and because all these bonds are symmetrical to one another, this is another example where we have a molecule that has polar bonds, but the molecule itself is not polar. What about asymmetry? Well, we've seen all these before. Water. Water's polar, water's polar, water's polar, water's polar. Why? Because water has polar bonds. The hydrogen and oxygen bonds are both polar, and the molecule is not symmetrical in 3D space. They do not cancel each other out. Same thing's true with ammonia. If you look at ammonia in 3D space, all the bonds are polar, but they again don't cancel out in space. So that molecule would be that molecule would be polar. And of course, hydrogen chloride, which we keep saying, has one side polar and one side not. So we have to figure out whether each one of these is polar. We've kind of already done these. Hydrogen fluoride is going to be polar because it has a polar bond and it's linear. Water's polar because it has this configuration where it's got polar bonds, but it's asymmetrical. The ammonia is polar. Here it is, 3D space. It is asymmetrical. Carbon tetrafluoride is just like carbon tetra, where is it? There, carbon tetrachloride. It's tetrahedral. It has some very strong polar bonds, but they cancel each other out, so that molecule is going to be non-polar. And carbon dioxide we've seen a couple times over. That's carbon dioxide is also going to be non-polar because it's got polar bonds, check number one, but it's not a asymmetrical molecule. It's a very symmetrical molecule. So therefore, it is going to be a non-polar molecule. So to summarize, if you have a polar bond, that means one atom is much more electronegative than the other, then the bond is going to be polar. If the bond is nonpolar, that means the two atoms have very similar electronegativities, maybe zero difference between the two of them, making a nonpolar bond. But if you combine the polar bonds with the symmetry, if it's asymmetrical and it has polar bonds, polar molecule. If it's asymmetrical and has no polar bonds, it doesn't meet that other criteria of having to have polar bonds. It's going to be nonpolar. And if it's symmetrical, regardless of polarity, you're going to have a nonpolar molecule. So you have to do this combination between, do we have polar bonds? Check yes or no. If it's yes, check for symmetry. And if it's no, you're done. And if it has polar bonds and it's symmetrical, they cancel each other out. That means there's no polarity to the overall molecule. And if it's polar bonds, but they are in an asymmetrical configuration, that means they're going to be not canceling each other out. So we're going to have a polar molecule. So this time you should be able to do the homeworks associated with molecular geometry and polarity. There's not a lot here to practice on, but of course, if you have questions, you can always ask in class. This is the last lesson in Unit 3. That means our test is right around the corner on December 19th. You have a great rest of your day. Toodles.